This video will be a review of two-dimensional polar and three-dimensional spherical polar coordinate systems. Okay, in two dimensions, we're very familiar with an x versus y graph, a standard two-dimensional graph for a two-dimensional point. So we can characterize a point in two dimensions by its x and its y coordinates in Cartesian, or alternatively, as mentioned in the previous trigonometry video, we can represent that in polar coordinates in terms of distance to the origin r and angle from the positive x-axis theta. So interconverting between these two values, r is the distance from the origin. It makes a hypotenuse in this triangle between x and y. So Pythagorean theorem, r equals square root of x squared plus y squared. Simple enough. And theta, based off of the angle that we have there, is equal to the arctangent of y over x. It's the angle at which the ratio of y over x gives you this angle. So be careful with the arctangent function because typically the range of this is defined over 180 degrees. So some calculators, some computational programs might only be defined over 180 degrees, maybe from negative 90 to 90, maybe from 0 to 180. But a lot of times in computer programs, you'll have to use this function called atan2, or something like arctangent 2, something that defines it over the full 360 degree range. Then x, converting back from polar to Cartesian, x equals r cosine theta and y equals r sine theta. No worries about the signs there. Those are all unique to specify. Then the ranges of x and y, as we know, are all real numbers. They go from minus infinity to infinity, each of them. But r is a square root, so the lowest value it can have is being at the origin, being a distance of 0 from the origin. And the maximum value it can have is an infinite distance. So being an unsigned distance, it goes from 0 less than equal to r less than infinity. And theta is periodic every 2 pi. So you could define this as, for example, 410 degrees instead of 50 degrees, but it just repeats every 2 pi. So usually the region that theta is defined over is just 0 is less than theta is less than 360 degrees or 2 pi. So that's in 2 dimensions. That's a slightly simpler case than what goes on in 3 dimensions. In 3 dimensions, we have our Cartesian x, y, and z. X is perpendicular to y, and both are perpendicular to z, which I have coming out of the board right now, represented by this arrow with a dot at the front of it. So in the xy plane there, so we have x, y, z in Cartesian, all of those going from minus infinity to infinity, as they did in 2 dimensions. Going to what are called spherical or spherical polar coordinates, we have the 3 values r, theta, and phi. I'll sometimes say phi, sometimes say phi. I don't know which is right, but I'm going to probably slip up and say both. Okay, so we have, just as we had in polar, we have phi is the distance or the angle between the plus x-axis and the projection into the xy plane of our coordinates here. So theta is the angle that our vector makes with the plus x-axis in the xy plane. And then if we look at if we rotate this kind of 90 degrees backwards and we get z coming out now, and this is the xy plane, theta is the angle that we make with the positive z-axis and the projection of our vector there to the positive z-axis. Okay, so our coordinates are theta and phi there, and r again is the distance from the origin to our point in 3 dimensions. So then r is the easiest to define as the square root of x squared plus y squared plus z squared, 3-dimensional Pythagorean theorem. Theta is equal to the arc cosine of z over r, the inverse cosine of z divided by r being this value again. And then phi equal to the arctangent of y over x, just as theta was in 2 dimensions. Don't ask why they chose to be theta here and phi there. They just did. We're going to have to roll with it. Same comments about the range of phi being 180 degrees versus 360 degrees apply here as well. Then the values, r can once again go from 0 to infinity. Phi, as theta did, can go from 0 to 2 pi. And theta can go inclusively from 0 to pi. The smallest angle you can make with the plus z-axis is 0 degrees. The biggest angle you can make is 180 degrees, pi radians. Then going from spherical back to Cartesian, x equals r sine theta cosine phi, y equals r sine theta sine phi, and z equals r cosine theta. You can work through the trigonometry yourself and convince yourself that that's correct. And as I mentioned, the range of all those in Cartesian is from minus infinity to infinity. So why all the hassle with this, you might ask? Just because some functions are more easily defined in polar or spherical polar than Cartesian. Some integrals and derivatives are more easier done in these coordinate systems. Sometimes it's more natural to express things in one system rather than the other. For example, if I've got a three-dimensional square box, it's pretty easy to express that in Cartesian. If I've got something that's spherically symmetric, like a hydrogen atom, where I have a very clear origin, like my nucleus, it's a lot easier to express that in spherical. So problems will come up as they go, but a very good lesson to learn in PChem, as in the rest of science, is that whatever system is most natural and easiest to express your system in and to solve it in is probably the system you should use.